Hello and welcome back. So today we're going to do experimental probability, and I'm going to apologize in advance. Might be a longer video. More importantly, I'm going to apologize for any mistakes I make with the mouth because it's a longer video. I'm going to do this in one take regardless. So your experimental probability foldable is actually yellow on your paper. It copies this way on mine. Anyway, experimental probability. We're going to talk about simple events, compound events, and making predictions. Now, just to refresh, whenever we're talking about probability, we have it usually displayed in a fraction. The number on top is always going to be, regardless of whether you're doing theoretical or experimental, it will always be the times, and actually put number of times true, over, and this is where it changes a little bit, the total number of experiments. So think back to theoretical probability. If we were to flip a coin, it would be 1 out of 2 for a probability of heads, and that's because heads is possible to be true 1 out of 2 ways. Okay, so theoretical is the number sense of how things work with probability. Experimental probability says what actually happens. Deck of cards. So theoretical probability tells me that 13 out of 52 of these cards are hearts. So 13 out of 52 of these cards, 13 out of 52 are hearts. And that reduces to 1/4, or 1 out of 4. So theoretical probability says 1, 2, 3, and 4. So I just pulled 4 cards off the top. I have a Jack of Hearts, a 5 of Clubs, King of Hearts, and Queen of Hearts. So my experimental probability is not 1 out of 4. My experimental probability is 3 out of 4. And that doesn't mean it's broke. That just means in the real world, this is what I got. Now, the more cards I draw, the closer I'm going to actually get to 13 out of 52 because I'm just pulling cards out of the deck. So eventually I'm going to wind up with a stack of hearts that numbers 13 and the rest of the cards. So it comes out. And you'll find that with all experimental probability. The more experiments you do, the closer to theoretical probability you get. Now, let's get on to an example. And I don't know that I want to do 2 examples. I think 1 is enough on this one, just because we have so much to cover in this foldable. So Jose rolls a number cube, and we all remember that a number cube is just a fancy way of saying a dice. Okay, so Jose rolls a number cube several times and records the results in the table shown. Use this information to find the experimental probability of landing on each number. Okay, well, remember the top part of our fraction, so each of these are going to have fractions. The top part of our fraction is always the number of times true. So let's look at this table. Table. Texans coming out. The number is going to refer to the number on the number cube. All right, so that's a number 1, that's a number 2, and then a number 4. Make sense? Frequency. Frequency is going to be how many times it landed on it. That would be the number of times it was true. Okay, so the number of times it was true. So landing on 5, the number of times true is 5. but we need to know our total experiments. So how do we find the total experiments on this table? Well, we have to add. So we're going to add all this row together of the experiments because we did 5 experiments there, 7 experiments, so that's 12 plus 11, 23 plus 9, 32 plus 8, plus 10. So he did a total of 50 experiments. He rolled this die 50 times. Okay. Well, number 2, how many times was it true? It was true 7 times, but 7 out of how many? That's right, the number of experiments didn't change. It's still 50. 3 out of, or number 3, it landed on that 11 times out of 50. On number 4, it landed 9 times out of 50. Number 5, it landed 8 times out of 50. And number 6, it landed 10 times out of 50. So we have just found the probability. Now you could show this in a decimal or a percent if you wanted to compare these numbers. Since they all have the same denominator, it's pretty easy to compare. I want you to do me a favor though. I want you to think about this. What number, according to experimental probability, is most likely to be rolled next? Okay, hopefully you paused and thought about it, and hopefully you came up with the number 3. 3 is more likely to be rolled because of experimental probability. If you notice, it was rolled more times than any other. And you don't know why. Maybe he's holding the number 3 up every time in his hand, and so it's more likely to land up. Maybe the sides of the dice are just a little bit off. Maybe one side of the dice weighs a little bit more. That's actually a way to get dice to land the way you want almost every time, is to weight one side. I don't advise doing it because that's cheating, and cheating is bad. Regardless, this is the experimental probability. And it basically puts the real world spin on the math we do to make sure that we're making accurate predictions. Down here in example 2, we're going to do the same thing. So you're going to look at the frequency and then add up all of those numbers, and you can find the individual frequency. If you want, go on ahead, pause the video, take a look at it, and see if you can come up with those frequencies all on your own. I, however, am going to move on to compound events. Now, a compound event is really just 2 or more simple events. And when it comes to experimental probability, life gets really easy, okay? So let's look at example 3. Example 3 suggests that Erica flipped a coin. That's a simple event. And she rolled a 6-sided number cube. Do we remember what what that's a fancy word for? That's right, it's a dice. So she flips a coin and rolls a 6-sided number cube. Use the data from the table to find the experimental probability of landing or flipping heads and landing on the number 5. Okay, so let's look down here at this table and let's figure out what's going on. So she's flipping a coin. What are the possible results of flipping a coin? Well, if I flip a coin in the air, I can land on heads or tails. So if she landed on heads, she probably put it in the top column or row. If she landed in tails, she probably put it in the bottom row. Makes sense to me. And now she rolled a dice. Well, up here it kind of makes sense because our numbers on the side of the dice are 1, 2, 3, 4, 5, 6. So if she had a heads and rolled a 1, I bet she put the number here in this little caveat. That makes sense to me. So let's take a look. We want to know of rolling a heads. So we're going to look at this heads column. And landing on the number 5. So here's my 5. Okay, where do those 2 points intersect? Well, they intersect right here at the 4. So I know that the number of events true is going to be 4. But now I have to find the total number of events. How do you think I'm going to find the total number of events? You got it. Just like I did before, I'm going to add all of the times I did the experiment. So the easy way I like to do this is I'll go across and then I'll go down. So 4 plus 3 is 7. Add another 5, that's 12. Add 3, that's 15. Add 4 is 19. Add another 5 gives me 24. Okay, now look at the next one. 3 plus 5, that's 8. Plus 9, 8 plus 9 is 17. Plus, wait, 8 plus 9 is 17, plus 3 is 20. Yeah, 20 plus 1 is 21. Okay, and when I add those up, what did I do wrong? Oh, I know what I did wrong. That's not a 9, that's a 4. 3 plus 5 is 8, plus 4. 8 plus 4 is 12, plus 3 is 15, plus 1 is 16. There we go. Now my numbers make sense to what I remembered. Okay, 4 plus 6, 0, carry my 10, 1, 2, 3, and 4. So my total experiments is 40. That means in this case, the probability is going to be 4 out of 40. And I can, of course, reduce both top and bottom by 4. And so that would give me 1 out of 10. So 1 out of every 10 times that she flips the coin and rolls the dice, she's going to come up with heads and a 5. It's not exact, but that's what the experiment is saying. Make sense? Why don't you go on ahead and take a look at example number 4. Example number 4 is fun. I like example number 4 because you're pulling cards. But it works the exact same way. You look for what they're looking for. So in this case, the experimental of pulling out a diamond. So I'm going to look at diamonds. And then spinning a 4. And where do they meet? Well, they meet right here at the 5. So I'm going to add up all of the probability or all of the total, and I'm going to wind up with 5 over whatever all of those add up to, reduce it as needed. Pretty simple. Compound and experimental is really simple. It's just more addition. All right, prediction. Are you ready for this? A prediction is, I'm going to use something different that I haven't said in all of my classes today because I like it. A prediction is a smart guess. And what I mean by that is I am making an intelligent guess based on information I have. Okay. Now I do want to refresh you just a little bit before we get too deep into this. I want you to remember what percent means. So when I write 30%, I want you to remember that these 3 individual syllables actually mean something. So the 30 is really simple. It means 30. Per is a math word. Do we remember what math word per is? I hope you said divide because per means divide. And then cent, if you think about cent, century, penny is a cent. Well, that always has to do with numbers of 100. So if you're ever trying to convert percent into a fraction, just remember what it actually means. 30% means 30 divided by 100. Should help you out quite a bit. Okay, so ironically, we are talking about the experimental probability that it will rain on any given day in Key West, Florida is about 30%. Maybe I got that number from somewhere. So 30%, 30 divided by 100. Whenever I'm making predictions with experimental probability, I really want to try to make them look like ratios. That way I can compare them and I have tools that I can use to make it happen. So 30 over 100. And now, what does the 30 mean? Well, the 30 means that is how many days it rained. And then the 100 is going to be the total number of days I'm evaluating. So let's look on. Out of 365 days, about how many days can residents and visitors expect to predict rain? Okay, so out of 365 days, I know my new total is 365 days. I don't know what this number is. So it's going to be X. All right. Now let's take a look at it. We're going to write it over here so we can do a little bit more. There we go. All right. So how do I get rid of this 365? Well, I have to multiply both sides by 365. Because if I put 365 up here, those cancel out. And so now I just have 365 times 30 divided by 100. You know, this kind of reminds me of something we taught you. And we taught you cross multiply and divide to kind of make it easier to remember. But that's what's going on here. We're multiplying both sides by the 365, and then we're just moving the math. That way, X stands by itself. It's isolated. Okay, so let's go on ahead and do this. 365 times 30. 0 times anything is 0, but I'm going to hold it here because that's my tens placeholder. 3 times 5 is 15, carry the 1. 3 times 6 is 18, plus the 10 is 9. So carry the 1. 3 is 9, plus the 1, 10. So 10,950. But I'm not done. I have to divide by 100. How many times does 100 go into 1? 0. Into 10? 0. Into 109. It goes into it one time. Leaves me 100. 9. Bring it down. 5. Goes into 95. 0 times. Bring it down. Goes into 950. 9 times. That'd be 900. It's going to leave me with 50, which is going to make me have a 0.5. So it'd be 109.5. Now remember, it asks about how many days. So about how many days wants to know a rounding. If it rains at all on one day, doesn't that mean it actually rained that day? It does. So what we need to do is we need to look at this 109.5 and then round it. So we have 109 with the 0.5. The 0.5 tells us we're going to round up. So out of a year, we can expect it to rain about 110 days. Okay, let's take a look at one more example, and then I've got to run because I'm getting a grumbly tummy. An airline's daily flight data showed a 2% probability that it was delayed. Now remember, 2%. 2%. 2 divided by 100. If the airline has 1,250 flights a month, okay, so 1,250 flights a month is going to be the total, so that's going to go on the bottom. How many flights would I expect to be delayed? Well, I'm in the same setup as before. I just multiply both sides by the denominator and then divide. So 2 times 1,250 and 2, 0, 0, carry the 1, 4, 5, and 2, 2,500. And now I'm going to divide by 100. But actually, I know that if I was to set it up as a fraction, I know that I can just divide out those tens, and that gives me 25. So if you have experimental probability, you can actually forecast a lot of different numbers based on what you see. And it's a really cool practice. It's actually something I use quite a bit in the real world. I know that approximately so much things are going to happen, so I kind of predict that that's what's going to happen next time. For example, my miles per gallon in the car I drive and the motorcycle I drive, they're not always the same, but the average is, so I know that the probability is very likely of when I'm going to run out of gas. And I make sure to get to the gas station before I get there. I hope this helps. I know I didn't do all of our foldable, but it should get you there. Also, don't forget, IXL has a bunch of lessons on this. Khan Academy has some great videos on how-tos. Don't feel like I'm the only place you got to look. That being said, please don't forget, click the subscribe button, leave a comment, let me know how things are going, hit that notification bell, And I'll see you in class tomorrow.